So, and it's a full, I don't know if I can make this full screen mode better now. Okay, first of all, thank you, Dr. Sargori, for the invitation, Neda, and thank you, Masood, for all the help with the techniques. Hopefully, we will not have any more security issues. I mean, this is physics, this is open research, so it should not be subject to any problem, hopefully. I'm happy to be here, and I want to share with you some interesting results and ideas about dense quark matter and the possible realization of inhomogeneous phases, and particularly one, the magnetic dual chiral density wave phase that I have been working with my colleagues, my collaborators, for a few years already. So the outline will be, well, we'll see why quark matter. Why do we really care about quark matter at high density, matter under string conditions? Why it has to be inhomogeneous? Then I will discuss the basics of the MDCDW phase and provide you some examples of why we think that the MDCDW phase could be realized at the core of neutron stars. Okay, many people have seen similar graph like this that describe the QCD phase map. We all know that with lattice QCD, we can explore only certain region where the chemical potential is zero. You know, we can go all the way to high temperature, but as soon as we have chemical potential, we have issues with lattice QCD. There are some improvement where they move a little bit out of the axis, but still not too far. And then we know we have nuclear physics. We know how to work with nuclear physics. So in the regime of nuclear physics, we know how to handle questions. I don't know if you can see the extreme because I see the pictures of people and I don't know how to change that. Hopefully everybody can see the graph. Okay.
So we can see it.
You can see it?
Yeah.
Okay.
Sure.
So if you go to the very large density region, so very high density region, the confinement works, and you can describe the theory with QCD. And we know that the phase that realizes there is a color superconducting phase. As a matter of fact, the color Frege-Log phase. So that part is also known. The main problem is when we go to a region of intermediate density, I mean, large, but not asymptotically large density and low temperature. And this region is being explored more and more by several experiments that some of them are planned experiments, some of them are already in the making, but still, we don't have experimental data to describe this region.
Sorry, Vivian, we are still in the first page. It's not changing.
What do you mean this first? You don't see the phase diagram?
I'm still in the presentation that is in the first one.
Vivian, you might be sharing a wrong screen.
What do you mean sharing the wrong screen? Okay, I see my presentation changing. So you don't? Sharing is paused, bring your share window to the front. Okay. So you don't see the change of the?
No.
Where are you? So what is what you see?
First page.
This is only the phase diagram and also some picture.
Okay, stop sharing. Let me share again.
Nothing. No, nothing.
Okay, let me share again. Okay. Do you see it now?
You are
Is it
in
in a neutron star and also
Yeah, but it does not change the page.
yeah. It
Don't
seems
put
so.
full
It's weird
screen.
because it was changing with me.
Don't pull full screen and let's see what happens.
No, okay, let me go out of full screen.
No.
Yeah, now
Now you see it or not?
Yeah, when you were changing the screen the last time, we were seeing it. I think it was right.
That's weird.
share again and now change.
This is the first page. Outline. Why quark matter? Why
Okay,
inhomogeneous? Yeah.
okay,
Yes.
but you see,
Now
I
try
hit
the
the
second
buttons
page.
and it does not. So let me do it here. Okay,
Yeah,
I will check. Do you
Now
see
this-
the
Yes.
phase
that's
diagram now?
Now it's okay.
Okay.
Yes. Yes.
So I guess I will have to change the slides from here, from the, okay, I figured it out. So, so what I was saying is that in the intermediate region is where we have a challenge because we don't have experiments to prove that region, and we only have what we observe from neutron stars that also happen to be in the region of intermediate densities and low temperatures. So the way to prove this region is by theoretical approach using effective models. So the rest of the talk would be related to one of these effective models, or one of these the phases that could be realized there. There are many proposals, and the only way to know if they work or not is by comparing their prediction with observables. And so that's the approach I'm going to have. The second thing I want to say is that there are many arguments in favor that the phase, if it is a quark matter phase, because it might not be a quark matter phase, it might be just a nuclear phase. But if it is a quark matter phase, that phase is inhomogeneous. And I will give you the arguments why that should be the case. So let's go to the next one. So why a quark matter phase? That's the first question. Well, we know that neutron stars are made mostly of neutrons with some composition of protons and electrons. And when the density, when you go inside the star, the density increases and increases. And there is a possibility that there is a transition from quark hadron from hadron to quark transition, so that at the core we can have quarks. This is a hypothesis, sustained by different models, but there is a very interesting paper that came up recently, and we saw the author giving a talk in Igor's seminar that that has obtained plausible arguments in favor of the existence of quark matter phases in the core of certain neutron stars. The arguments are such, so the calculations they did, which are made by interpolation of the equation of states, but independent of, model independent. And in addition, constrained by the parameters of the tidal deformation and by reaching 1.97 solar masses. And what they found is that the behavior of the equation of states using these interpolations that they did pretty much indicate a change, a transition to a quark matter phase. They used speed of light interpolation method. And what they found is that the quark matter phase is favored, particularly in very massive stars. So in the core of very, very massive stars. So this is very, I found that very interesting because it's a model independent result that, a model independent result that support the idea of quark matter. And when they, I go always in the wrong direction. So when they consider the cores of these supermassive stars, they found that they were consistent. So they found large chords with their calculations. All of them, or most of them, were constrained by a speed of sound of near the conformal limit. So below or near the conformal limit. So the argument or the conclusion of this paper is that quark matter is actually not an exotic thing, but rather standard. And that is an argument in favor of what I was saying, that there might be stars with quark matter in the core. So it's important to investigate what type of quark matter realizes in the core. What is the phase of quark matter?
Sorry, what is the meaning of a standard here? Standard is...
Standard in the sense that they found, so what this paper found is that all the massive stars, they use this speed of sound interpolation method, among many others, but they use that one. It's a method they developed. And what they found is that practically all the massive stars that satisfy the constraints that they impose were had a quark matter core. That's the main result of the paper. So that's what they say is rather standard and not exotic, because there are massive stars we already know. We have observed that. That sense.
Thanks.
Then there's another element that is also very important to be considered, and we should keep that in mind, which is the magnetic field, because we know that star has magnetic fields, very strong magnetic fields, some of them very, very, very strong magnetars. In the surface, we measure the field. We have been able to measure the fields. In the core, we have not been able to measure the field directly, but there are estimates of the values of the field, and we know that it's even higher than in the surface. So this is an element that should be considered when we study models for describing the core of neutron stars, because magnetic fields would be present, and we want to see what are the effects of this magnetic field, what phases would be affected or favored by the presence of a magnetic field. So why inhomogeneous phases? Okay, so we already see, okay, quark matter is not a crazy theoretical idea. There are arguments in favor of it, but there are many phases of quark matter. So my argument is that probably the phase would be inhomogeneous. So the reason for that is what I want to discuss. And for that, we need to see what are the type of pairings that can happen among quarks when you have a Fermi surface. So when you have a Fermi surface, the regular, the most common is a condensate that appears pairing between quarks, is the chiral condensate. In general, pairing between Fermis, right? So if you have, the chiral condensate is a condensate that pairs particles and antiparticles. When you don't have any density, of course, they are very close to each other because you have the Dirac sea, and the difference in energy is very small. But once you have density, you have to excite the antiparticles all the way to the Fermi surface for them to pair. And of course, there is an attractive interaction because particle antiparticle. But you need to excite them, and of course, it costs energy. And eventually, if the density is large enough, that energy is such that this is not energetically favored. So this is a possibility, but it's not the one that is favored at intermediate to high densities. And this would be an homogeneous condensate because it pairs particles, antiparticle with opposite spin and opposite momentum. The other possibility that can happen when you have a Fermi surface is a Cooper pairing, because there is the anti-triplet channel of QCD is attractive. So you can have pairing between quarks of different flavors and different colors. And that actually is favored when you go to very, very high densities. This is the phase that is realized, is color flavor lock, where all the quarks pairs, all the flavors and all the colors pair between them. So this is a possibility. It will produce a condensate that is homogeneous, and it has spin cancel out, but it's only favored at asymptotical densities. So actually, neither one of them is the best candidate for intermediate densities. Well, for the chiral condensate, I was already explained the reason. It's energetically unfavorable when you have densities that are increases. But for the Cooper pairing, the thing is that once you take into consideration the constraints coming from neutrality and neutrality in electric and color neutrality and beta decay constraints, when you take that into consideration, the Fermi surface of quarks of different flavors are different. So you have a mismatch between them. And eventually the pairing in this form, homogeneous, is not favored. A way out of that is forming inhomogeneous condensate of Cooper pairs. And this is a possibility, and we cannot just roll that out. So this is an interesting possibility. So that would produce spatially modulated quark-quark condensates, color superconducting condensates. And but this is not the one that I want to consider today, but I want to be sure that we don't rule out, because this is a possible option. The other type of pairing, and this is the one that I will concentrate the rest of my talk, is the density wave pairing. And that is a pairing also that occurs at the Fermi surface between a quark and a hole. And because it's quark and hole, you don't have Fermi surface mismatch between them. And this pairing is for quark and a hole, so of the same momentum. So the momentum of is non-zero. The spin is opposite, so it's a boson, but it has a non-zero momentum, so it's an inhomogeneous condensate. And this condensate is favored over the homogeneous chiral condensate, and also is favored over color superconductivity R' NC. So this is the one that we are going to concentrate. The possibility of a phase that pairs quarks and holes at the Fermi surface with a net momentum, so inhomogeneous. So I will be talking about a particular phase of this type where
Sorry, Vivian.
Yes.
I have a question about your previous comments about inhomogeneous condensate. I want to ask that does your arguments are general? I mean, for example, does it depend on any, for example, magnetic field or any other extra parameters that favor this phase, or it happens in more general cases?
Okay, so my argument is general in the sense that it's hard to avoid inhomogeneous condensates. That's the first argument I want to make. That when you consider inhomogeneous versus homogeneous, it seems that homogeneous condensate eventually are not favored for different reasons, depending on if it is a chiral condensate or a color superconducting condensate. And the solution is considering inhomogeneous condensate. Now, external parameters like a magnetic field may help or not. You'll see that in this case, it will help the condensate, the inhomogeneous condensate. And I will explain that in the case of the density wave pairing, how a magnetic field actually helps the realization of this condensate. And the way it does is because it creates topology. So we'll see that. But the argument about inhomogeneous, you go to inhomogeneous from many different approaches. So quarkionic matter also, you come from an argument based on QCD and the behavior of where you have confinement, where you don't have confinement in the Fermi surface, and inside or outside the Fermi surface, and still you get to an homogeneous condensate. So it seems that it's unavoidable, and that's my argument. But which one in particular depends, and how it will be affected by a magnetic field also is a question, and I will discuss that in this case, the density weight type of pairing, the magnetic field actually helps the condensation, favors the condensation. So this is the phase that we call magnetic dual chiral density weight phase. So what is that phase about? Okay, so the phase comes from a theory of a non-Bujonian Lacinier theory, which is, this is a two-flavor non-Bujonian Lacinier model that you can consider is one of the effective theories you can use to describe what matter at intermediate density. So you have a baryon density that is non-zero. We assume that is 2, 3, 4 times the saturation density, nuclear saturation density. And we describe the theory by this model. So the quark interactions are represented by these 4 Fermi interactions, typical of non-Bujonian Lacinier models. But then we also introduce the electromagnetic interaction, because we are going to consider this theory in the presence of a magnetic field. So we have electromagnetism described here by the regular Maxwell term. We have the interaction with the magnetic field and the electromagnetic field in general that we can consider that is small, so we can neglect it, but still we have the magnetic field in the background. And then, and we use an ansatz for the ground state. We say that the pairing between quarks would be a chiral pairing that we have, it would be described by a complex condensate, because we have pairing of psi bar psi, but also pairing of psi bar gamma phi psi. Okay, and it's inhomogeneous, so you see that it depends on x. So actually, because of the magnetic field, this Q is going to be, and you can prove that is Q is preferred to be along the direction of the field, and we are taking the magnetic field in the z direction. So Q would be a vector only in the z direction. Q is actually a pseudo vector, as you will see. So you introduce this condensate here, and find the mean field Lagrangian, and when you do that, you see that the mean field Lagrangian has a mass term that is complex. Okay, so I mean that's. It's not convenient to work with a complex mass term, but you can do a transformation to get rid of that term, and that's what was done by the authors who did this study, Frolov et al. And also Tatsumi. And by doing that transformation, what happens is that your Lagrangian acquires a regular mass term, but also acquires this gamma phi, gamma 3 addition term proportional to Q in the covariant derivative. So now you have a Lagrangian that you can work regularly because it doesn't have any weird mass term, but it has a regular mass term, it has this. And when you study it, so this is a transformation that you need to do.
Sorry, Vivian.
Yes.
I miss why you introduced this chiral transformation. What's the use of this transformation?
Okay, so this is a transformation that you can do this transformation. It's a local transformation on the fields, and it's just a way to rewrite the Lagrangian in a more convenient way. You can always do this transformation, right? Mm-hmm. And when you do it, the Lagrangian, you get rid of the term that you had, now the mass, this term that was inconvenient, to work with it because it depends on Z. Now it becomes a regular mass term. You can do the transformation by yourself and see it. Mm-hmm. You get this regular mass term, and then you get also this other term in the covariant derivative. And when you study this theory, and you find the fermion spectrum for this theory, you see that the spectrum is asymmetric for the lowest Landau level particles. So what do I mean by that? Well, higher Landau level particles have the spectrum that is symmetric. What do I mean? Well, that you have a plus and minus energy, so the particle and the antiparticle, but for higher Landau levels. But the lowest Landau level, that's not the case. You have epsilon plus minus, but because of this Q/2, which is the inhomogeneity, this is the modulation of the condensate. Because of it, this spectrum is not symmetric anymore. You don't have plus or minus the same energy, right? And once you have, so if you have a Hamiltonian whose spectrum is asymmetric, that is a sign of non-trivial topology. Okay, this is
May I ask a question here? Sorry.
Yes.
Can I ask a question?
Sure.
You have written the mean field Lagrangian as this form, and what did you do with the I don't know, the FF dual term that happens when you do this Weinberg transformation?
Okay, I'm going to talk about that in a moment. So at this point, what I'm saying is the things that were found by other authors, okay? But then they missed at that point. So we'll see that term in a moment.
So it exists in mean field like Lagrangian. It exists here, actually, yes?
It does exist, yes, actually. Yeah, because the thing is that this transformation, what I'm showing you is what happened with this transformation for the Lagrangian, but I'm not saying anything about the measure, the fermion measure in the integral. And the fermion measure is not invariant under that transformation. And you have to take that into consideration. But before, I wanted just to call attention that we have this asymmetric spectrum, which is very important because it tells us that there is non-trivial topology in this system. So when you are right. I mean, when you take into consideration that, okay, let's see. When you take into consideration that the spectrum, I missed it. I went over to, so the transparencies are not in order. So when you take into consideration that the measure is not invariant, and you calculate this Jacobian, the Jacobian actually, this determinant is ill-defined. So it needs regularization, and you have to be careful to do the regularization in a way that is gauge invariant. So when you do that, you find a contribution that is an anomaly. This is the chiral anomaly to the Lagrangian. So now the Lagrangian, this is what you were saying. Now the Lagrangian will have the terms that I said, you see, plus this anomalous term, which is very important because this anomalous term, if you integrate out the fermions to find the effective action for the electromagnetic field, you get a theory that is not described by the regular Maxwell equation, but by axion electrodynamics. Because you have these that anomaly gives you terms like this, which is an anomalous charge, and terms like this, which is an anomalous Hall current. Okay, it comes, these two terms, they come, both of them, from this term that appear when you take into account the measure. Okay, so let me go to this transparency.
Let me ask another question here. Didn't you just fix the gauge in the main Lagrangian at the start? Didn't you just fix?
I didn't put the gauge, but yes, you have to fix the gauge. When you do the calculation, of course, you have to put a gauge.
So if we fix the gauge and we just have the magnetic field, the FF dual term should be doesn't exist because the electric field is 0. So why does this?
Oh yeah, so the background electric field is 0, but you are not saying that the electromagnetic field, you might have waves. So you see the electromagnetic field as you can consider that it's a small electromagnetic field, but in that case, that term will appear because you can consider So when I do this expansion, here I'm making expansions in powers of the electromagnetic field, right? Of A mu. And you can consider that you have a perturbation over the magnetic field. And that perturbation, it will give you contribution to this term. You're right. If you don't have that perturbation, the magnetic field alone cannot give you anything here. So you need the magnetic field plus electromagnetism, okay? So that's what you have to consider.
So we have a fluctuating field over our background, yes?
Exactly.
And do you, okay, thanks, yeah.
You understand?
Yes.
Okay. I missed this transparency. I think that I should have put it before. So this transparency is interesting because it shows you, I think it answered one of the questions of one of you, I don't know who was the person who asked this question, that once you have a magnetic field because of the spectral asymmetry that I told you that is topological, you get an anomalous contribution to the thermodynamic potential given by this term. This is an anomalous term. Normally you don't have anything like this, you know, and that will produce an anomalous baryon number density. But as importantly, and all this is because of the magnetic field. No magnetic field, you will have nothing, right? The spectrum will not be asymmetric and you will have nothing like that. As importantly, you can see here that the solution, so these are the values, the minimum values for the parameters M and B. So the mass, the magnitude of the condensate, and the modulation of the condensate. B appears even from very low chemical potential. So this condensate exists all over for all chemical potential. Here is insignificant, right? Because the mass is practically the vacuum mass and B is very small. Once you get to this region of where normally you will have the transition, phase order transition to symmetric phase. Here you don't have that. You have a transition to the homogeneous phase, which is favored over the symmetric phase. Why? Because of this term. This is a negative term in the free energy. So because it's a negative term, it tends to decrease the energy and it favors. This is the answer to that question. Why this, you know, the magnetic field is creating, is producing a phase that is favored over the chirally restored phase. Why? Because of this. Because of the anomaly. This is important to underline. Okay, so we have this, and that implies that the properties, the electromagnetic properties, the electromagnetic transport has these anomalous contributions, and as interesting, the whole conductivity has an anomalous, you know, so we have an anomalous whole conductivity, which by the way is similar to what you see in wild semi-metals. So it's, you know, properties there are resemblance between the properties of this system and the properties of condensed matter materials, topological materials. Okay, so this is an interesting property of. There is also magnetoelectricity because of these anomalous terms. So an electric field can produce a magnetic polarization, and vice versa. A magnetic field can produce an electric polarization. So we answer. So these are the main properties of the MDCDW. But now the question is, okay, interesting. It's an interesting. It has its topological properties, but is this really a phase that has any prospect to be part of, you know, to be one of the neutron star core phases? And the answer to this question, of course, have to be answered or, you know, checked by observations or tests that, you know, tells you, okay, this phase can be stable. Because by the way, this is important to keep in mind. The magnetic, the MDCDW phase is a single modulated phase, right? That means that the modulation is in a given direction, is in the direction parallel to the magnetic field. that single modulated phases have an issue with the stability when you put any temperature. So single modulated phases has what is that the fluctuations about the condensate can erase the condensate, can erase the long range at any temperature, no matter how small. So this is important because what's the point to say, oh, this is an interesting phase, it has all these properties, but if I put it in, if I assume this is a phase in a star, the star has a very low temperature, but it's non-zero. So if the phase has a, it's not a good candidate, okay? Because it will disappear at any final temperature. The fluctuations will erase it. And as a matter of fact, this is what happened with quark matter cannot have the long range order at final temperature. You can have a quasi long range order where the square of the condensate is non-zero. It has a modulation, but long range order disappears. So this is an important question to answer, right? Also, you want to be sure that the MDCDW is not in contradiction with observations like the two solar masses and maybe other constraints. So this is what I'm going to discuss now. So first, let's talk about stability against fluctuations. To answer that question, we need to study the low energy theory of the MDCDW. So you need to, so you have to, you have the order parameter, which is a combination of the two condensate that I already showed you. And in order to obtain the low energy theory, you have to do an expansion, actually a generalized Ginzburg-Landau expansion of the thermodynamic potential in powers of the order parameter and the derivatives of the order parameter. And of course, that expansion would have to be invariant under the symmetries of the original theory. And the original theory has chiral symmetry, it has rotational symmetry around the axis of the magnetic field, and has translational symmetry. This is before the symmetry break. So these are the points that you need to make in order to construct the low energy theory. So we did this Ginzburg-Landau expansion and in powers of the order parameter and the derivative, and this is what we've obtained. So this expansion obeys all the symmetries that I told you before. The order parameter is a complex order parameter, you know, because that's the case we're considering the MDCDW. But I want to call your attention that there are new terms in this expansion that will not be normally if you have no magnetic field. So we have two types of new terms. So in the absence of a magnetic field, you will have terms like this. So if you have a complex parameter, for example, if you consider the DCDW phase, no magnetic field, you will have this, etc. Okay? Powers of M and derivative of M. Once you have a magnetic field, you can have terms that come from replacing the gradient by the projection of the gradient with a magnetic field. So you have this term, this is a regular term if you don't have magnetic field, but now you replace the gradient by projections along the magnetic field, and this term will give you this new term. This is a new term that normally would not be. Same thing for here. This one can be written as this when you have a magnetic field, because you have a vector and then you have a projection that you can construct scalars in this way. But in addition, in this case, we have terms that are absolutely new. Terms that are, as you can see, linear, not linear, odd in derivative of M. And these terms, in order to separate them, we put coefficients B to distinguish them from the rest. First of all, they only exist if you have magnetic field, but more than that, they are connected to the asymmetry. So the origin of this term is topological. The A terms are not topological. They will come no matter what if you have an external magnetic field. But the B terms will only be present because of the topology. How do we know that? Well, you can rewrite this when you took the ansatz that we use it for the MDCDW. This expression can be written in this way. And you can see that the B terms are all odd in Q. Q is the modulation, right? And in order for these terms to exist, the only way you can find terms like this is if you have the asymmetry in the lowest Landau level spectrum. Because this term being odd in Q, if you change Q by minus Q, this term is not invariant. But if you only have the spectrum of the higher Landau levels, so if the spectrum were of the form symmetric type of a spectrum, you change Q by minus Q and nothing should change. And you can check that the spectrum of a high Landau level being symmetric in the thermodynamic potential, when you change Q by minus Q, that part remains the same. One becomes the other, one energy becomes the other, remains the same. But that does not happen with the lowest Landau level. So, and I told you already, lowest Landau level spectrum is the asymmetric spectrum, and it's the one that is related to topology. So these terms, because part of the lowest Landau level spectrum is being asymmetric, it has a symmetric and asymmetric, antisymmetric component. And the antisymmetric component is the one that produces this. So these terms are purely topological. Yes?
Sorry, I wanted to ask what is the relation between, for example, A4N2 to A42 with a superscript of 0 and 1.
Okay, yes,
Yeah.
okay. So A420, we distinguish them because, as you can see, this term it has a gradient, but it does not depend, the structure does not contain the magnetic field. So normally, without magnetic field, the A41, for 2, the 6,2, but with a 1 super index, those terms will not be present. But they are present and they are distinguishable from here. And you'll see that they play a very important role in the stability. You'll see that these terms are essential for the stability of the phase. So the difference is that they have a separate coefficient because they correspond to a different structure. This structure and these structures are not the same, because this is only the projection of the gradient over B, while here you have the 3 components. So that's why they have different coefficients, and you can find the coefficients by calculating, from the thermodynamic potential.
Yeah, I understand that, but where did that go into the next formula?
Okay, these terms here, they do not appear in this. When you see, I didn't put any super because the A42, okay, is in another transparency. Let me show you here. The A42 is the combination of A420 and A421. And the A62 is the combination of A620 and A621. So what it means is that for the minimum equations, this separation is not relevant. So you can write F in terms of the sum and only the sum. It does not depend individually of them. It depends on the sum. So when you calculate the minimum equations, you don't care about the fact that it has 0 and 1. It doesn't matter, okay?
Mm-hmm.
But they will be important. You'll see that in a minute for the fluctuations.
Thanks.
Okay? And it's good that you are asking me because this is calling attention about something very, very important. Okay? So, okay, so the A1 coefficient, I just want to summarize, the A1 coefficients are related to the presence of an external vector, the magnetic field, but they are not necessarily connected to, they are not connected to the topology. So they will exist even without topology. But the B coefficients are only present because of the topology, non-trivial topology of the theory. And now, what I'm doing here is just looking at what is the symmetry breaking that occurs. So you can find the solution as the solution of the station. And there's a non-trivial solution for M and Q, which tell me that there is a breaking of part of the symmetry. So this solution will break chiral symmetry and will break translational symmetry along the Z direction. So because we have breaking of these two symmetries, spontaneous breaking of these two symmetry, we're going to have, in principle, we are going to have two Goldstone bosons that will define the fluctuations. You know, these are the fluctuations, the origin of the fluctuation will come from pions and phonons because these are the Goldstone bosons of this theory. Okay? So in order to study the fluctuations, now what we do is we perturb the order parameter with these fluctuations. So I am telling you that we have fluctuations due to the chiral and fluctuations due to the translation. So I perturb the order parameter with these two transformations, right? And see how it transforms. And then we can see that they get combined in this way. So clearly you can choose tau and chi, you can choose transformations such that they cancel each other. And that tells me that they are locked. So one of them, so both of them are not independent because you can have a combination that does not do anything. And there is another combination that will transform the order parameter. So you can choose any direction. You can say pion or phonon or a combination. For simplicity, we consider the phonon. So instead of two Goldstone bosons, we only really have to consider one fluctuation, one type of fluctuation, and that would be the phonon fluctuation. And considering that, you can construct the free energy of the phonons. And this is important because you need the free energy of the phonons to see how the phonons will affect the average of the condensate, which I'm going to show you in a moment. So the free energy of the phonons, first of all, I want to call your attention that is asymmetric, anisotropic, which is not a surprise, right? Because we have a magnetic field, so it's expected that you will distinguish parallel modes to the magnetic field and perpendicular modes to the magnetic field. On top of that, the condensate also create asymmetry, right? So that is not a surprise. What I want to call your attention is that we have the presence of these. So these V, Z, and V perpendicular square are the square of the group velocities in the system. And normally, this B perpendicular, normally I mean without magnetic field, this B perpendicular will not be present. How to see that in an easy way? Well, look at the expression of B perpendicular square in terms of the coefficients. This combination here, so if you don't have magnetic field, all the B coefficients and the A1 coefficients are 0. All of them. You will only have this combination. Let me show you that this combination is exactly, so look at this. So if I don't have magnetic field, all these B are 0. And I have, out of the stationary equation for the modulation, I get that this combination is identical to 0. Okay? And the M that I am using here, so this is constructed on the condensate. So using M and Q solutions of the stationary equation. So this combination is exactly the one that you will have identically 0 in the absence of a magnetic field. And only because we have B and A, one type of coefficients, this is not 0 anymore. And this is what I want to say, that the A1 coefficients are not relevant when you look at the solution for the minimum, but they are relevant when you look at the fluctuations and how that changes the spectrum of the fluctuation, because now the spectrum is anisotropic, but it's not soft. Let me put it in this way. It's not soft in the perpendicular direction. Without magnetic field, you would not have this K perpendicular here, because B perpendicular square would be 0. And it would be soft. It would be only fourth order in the momentum perpendicular, which means it's soft. That is the reason why the single modulated condensates, in the absence of a magnetic field, have problems, are unstable. Let me explain you a little bit more so you can see why. So, okay, so this is the spectrum that comes from here. We now can calculate how the fluctuations affect the average of the condensate. So for that, you calculate the average when you have fluctuations. So the condensate is perturbed by the fluctuations, and you average that, and you can show that it is proportional to this, that can be written in this way. So if bottom line, what you need to find is the average of QU squared. And this can be calculated from the spectrum, and from the theory of the fluctuations, from the free energy, and it is finite. If this is finite, so this is non-zero, okay? If it was not finite, so if it was like when you have no magnetic field, it will be, instead of finite, it would be infinite. It will have an infrared divergence. And in that case, of course, if this is infinity, e to the minus infinity goes to 0, that is what happens when you don't have a magnetic field. The long range order does not exist. The fluctuations erase it, and they erase it at any finite temperature, no matter how small. This is what is known as Landau-Pierce instability. So the magnetic field cures the Landau-Pierce instability in the MDCDW phase. It cures twice. It cures it because of the A1 coefficients, right? That I show you that they are present even if you don't have topological features in the theory, but also because of the B coefficients that are topological in origin. And both of them makes this B perpendicular different from 0, and therefore a finite long range order. Okay? So this is the first test that I said. It passed the test. The MDCW phase is stable at relatively low temperature because there is no Landau-Pierce instability. Obviously, if you increase the temperature, eventually the temperature will even erase the condensate. So it will create, the fluctuations can be so large that maybe some of these coefficients will go to 0, and then we're in trouble again. But that's a normal thing. But at least for low temperatures, we are fine because of this feature that I just proved. So that's the first test that I mentioned. Test number 2 is, how about the solar mass? 2 solar masses. We know that there are stars of the order 1.97, maybe a little bit even more than that from some recent measurements, observations. So can the MDCDW phase be compatible with that or not? And the answer is yes. We did that some time ago, and we consider MDCDW phase, but with neutrality, because in general, this phase is not neutral because you have U and D quarks with the same mu, so it doesn't have neutrality. But if you impose neutrality, you have to put some electrons, and that's fine. That's what we did here. You study that system, and we calculated. We found the equation of we assumed that we have a hybrid star, so we had transition from nuclear matter to quark matter in this phase. And when we calculated the equation of a state with very, very small, we didn't have to put very large vector interactions, okay? Because of course, if you turn very high vector interactions, you can go to any mass. You can make the equation of a state very stiff, but we didn't have to, and we reached the 2 solar masses with very reasonable values of GeV. So that's another test that is important, and it did pass that test. It's not inconsistent with the observation of 2 solar masses, neutron stars. One more test that it should pass is thermal properties. Are the thermal properties of this phase consistent with those that are known from stars? And this is a work in progress, and I'm going to say almost nothing, but it's interesting. I just want to mention that this test also seems to be passed, at least part of the test. The test can be more, can be expanded, but we are considering the limit that was established by a paper of Cumming and other authors for the heat capacity. So the core heat capacity should satisfy some lower limit, should be bigger than that limit. And the authors of that paper show that the CFL, the color flavor lock phase, does not satisfy that limit. It has a small component of electron, but it's not enough to reach out beyond the limit, the lower limit of heat capacity. So CFL is discarded. No surprise, because we know that CFL actually is probably not the phase that realizes in intermediate phases. But what about the MDCDW? Well, what we are finding is that it does satisfy, is compatible with, consistent with this limit. And we are working on the paper. It should be out very soon. So this is another test that also gives me confidence that this phase is should not be discarded. Of course, there are many other things that need to be done before we can be sure about it. But certainly this is really reassuring. I don't know if I mean, this is the comparison with some topological materials, but I think I am running out of time. So I will go back unless if you are interested in knowing about that. So in summary, I hope that I conveyed the message that the MDCDW phase is a viable phase at intermediate densities. There might be others. I mean, this is not, I'm not claiming that this is the phase that realizes in the core of neutron stars, but certainly it has already passed a few tests. So so far it's a viable phase because it's compatible with a few astrophysical constraints. Of course, we need to connect it to more measurable observables, and hopefully they will be available in the near future, because with the merging of neutron stars, we are learning a lot, and also with electromagnetic signals. So the multi-dimensional astronomy that we have now will produce a richness of observables that will help us to keep testing and discerning if this is the phase or maybe other phases would be more favorable. And the other important thing is I would like to study, we are interested in keeping a study on all the consequences of the topological properties, and also, it's interesting because we are learning from condensed matter materials some properties that inspires us to look for those things in the MDCW phase, and hopefully vice versa. Maybe we will do things here that will create ideas for people in condensed matter. That's it from my side. Thank you very much.
Okay, thank you very much for this nice talk. Now we have time for questions. Are there any questions? You can raise your hand when you have questions. Mm-hmm.
Yes, I have a question.
Any question? Yeah, please, Farid.
Vivian, I was thinking about the shape of this MDCDW phase. You told us that we have some kinds of quark matter arranged in periodic shape, yes? Somewhere we have...
Quark matter, repeat what you said, I didn't get what you said.
in the periodic shape, I mean, you have somewhere have a bunch of matter, then you don't have, then you have some in terms of Q, yes? This is the shape of this space.
Shape. That's what,
the
shape. What
form
do you
of,
mean by shape?
I mean the realization of this mz in terms of space coordinates. You wrote mz as me to the iqz, yes? This brings us the realization of your of this matter as the shape of, for example, you have some bunch somewhere, and then this repeats in the z direction. Is this correct?
Okay, so no. So what you have is a condensate that is like a crystal type of condensate.
Mm-hmm.
What you have is the background has a condensate that, you know, because it's a e to the kz, if you move in the z direction, you will have the background is, the condensate is larger and then smaller, and then, you know, it's like a wave. That's what is called chiral density wave. But if you move in the other direction, nothing changes. So whatever the magnitude of the condensate is at a given z, if you move along x and y, it's the same, because it does not depend on x and y. So in that sense, it's like a wave of, the background looks like a wave in terms of in the space. It's spatially dependent or spatially inhomogeneous in the z direction. That's what this, but this is the background. And then you have excitations, you know, quasi-particles about that phase, and then you have fluctuations, etc. So that is what you were asking?
Yes, yes. And I have another question about the magnitude of this Q. Is there any limit on this Q, for example, constrained by the size of the system that this phase constraint in that, or some
Q or B? B is Q over 2. Okay. So so B or Q is obtained from the minimum equations that I show you. So this, what you see here is a plot of, for a certain magnetic field magnitude as a function of M and B as a function of the chemical potential. And you can see that B increases with, so it increases with the chemical potential, but very slowly. And then you have a sudden increase when you reach the region where normally you will have, you know, chiral restoration. It increases and jumps to relatively high values, but it always remains below the chemical potential. Okay, it always remains below the chemical potential. So you don't have any particular constraint from the theory, but when you find the solution of the minimum equation, that's what you get. Okay.
So I see Hossein has also a question.
Mm-hmm.
You can unmute yourself.
Yes. I have two questions. One is a general question about these phases. I'm asking this question based on something that I know in solid state physics. Maybe I'm wrong, I don't know. That existence of these phases like spin density wave and charge density wave and etc. is somehow based on a fact that no one has ever come to another, I don't know, state via variational methods to have the lower energy that these states have. Do we have something like this in quark matter, and these phases in quark matter, this for the phases.
So what you're saying is that this phase not necessarily has to be the lowest energy phase. That's what you're saying. But there might be others.
Actually, yes, and I don't know. Based on the work of people that has done in solid state physics, no one has ever found that via variational methods that some states has lower energy than these phases. Do we have something similar like this in?
No, that I know. And also, I want to say that keep in mind, maybe what you're talking about are phases, modulated phases or inhomogeneous phases of this type, but without magnetic fields or without topology. And maybe, I don't know if this is what you are referring to, but maybe what they refer is to what I said, that those phases are not stable. Typically, they are not stable. So they you know, anything can, any small temperature can erase them. But I cannot say this is the most favored phase, because how do you prove that? Think about it. There are so many possibilities. Somebody can come tomorrow with a better ansatz and say, okay, this ansatz, I can prove that when you consider this ansatz for the condensation of the quarks, using the same pairing, but this different answer. There are answers that are not density weight, for example, and they are already present. So suppose somebody say, okay, I have this other answer, and when I study the theory, is energetically favored. Or somebody can come and say, this phase of color superconductivity, also inhomogeneous, is energetically favored. That is possible. I am not claiming this is the, because how do you prove that? You have infinite, almost infinite many different options to check. So I think that the best strategy is, I mean, I can tell you that this phase is favored over the chirally symmetric phase, for sure, that is proof. I also know that topology is something that produces robustness in the properties of phases. So this is a topological phase, so it will not be so easy to disturb it and eliminate it. But instead of comparing the energy of phases, which is a way to do it, but it would be a very long way, because how many phases can you compare? I think it's better to look for observables, and you know, the type of strategy we're following, which is this phase consistent with this observable, with this other constraint? And ideally, we would like to see if we can predict effects that will only be possible in this phase and not in a color superconducting phase or another type of inhomogeneous phase. You know, this is work for the future, but that's the ideal way to discard this phase or not. And that is true for any phase that you can come up with, okay? For example, I can tell you, if you go and consider an inhomogeneous phase that is based on a real condensate, this is a complex condensate because it has these two components, but a real condensate, I can tell you that that phase is going to suffer the Landau-Pilz instability. So it's not a good candidate, because even if it is realizable, it will disappear at any temperature. That's not a good candidate for the core of a neutron star. But there might be other candidates that are interesting, and the only way to know is either by checking and comparing the energies, but as I said, that would be a long way, because how many phases you can compare? Or what we're trying to do, which is looking at the consistency of this phase and the properties it has with observables and constraints that come from astrophysics and from other, you know, also from other calculations.
Thanks. I have another question about one of your articles. Can I ask that? About your paper on novel topological effects in QCD?
Mm-hmm.
There was a part that you somehow relate and compare this charge, that comes from axion QED, and you compare it to the Atiyah-Patodi-Singer's invariant, and you somehow said that they have they are the same. I don't know. I don't see any relation between these, and you somehow say they are the same. They have.
Well, because you can calculate. I don't have here the formulas to show you, but you can calculate that invariant. It exists here. You know, you can see that
same in value, but I don't know. They don't have any relevance to each other. They are not. So I don't see the direct connection.
Okay, the bottom line is that you have an axial anomaly, right? And you can find you can work with the axial anomalies in the integral and obtain rewrite in a way that you can see that it satisfies the same equation as the one that you have in that invariant. You can find the invariant in this case. So it's topological. The origin is topological, and here you have this anomaly that is a topological term. So by manipulating it a little bit, you can obtain something that is the analogous of that. Okay, the analogous of that I say because kappa would be constant, because the theta would be constant in that case. You would not have theta. So here is like a density of that, but it's very similar. So I would say the origin is because that term has an topological origin, and here you have also a topological origin. Once you have that anomaly term in the effective action, it's straightforward to show that. I mean, I can do it. I don't have here the questions, but I can show it to you. I mean, we can have, if you want, a discussion after the seminar, or another day, and I can show it to you so you can understand it if you want. Okay, I'm happy to help you with that.
I will. Thank you.
Mm-hmm.
Okay, thank you. I have also a question.
Sure.
Yeah, you say that the origin of this topological effect comes from the fact that we have an asymmetry in the energy dispersion, the lowest Landau level. How essential is this fact that the asymmetry appears only in the lowest Landau level? And are there any other examples where we have asymmetry in other Landau levels, higher Landau levels, and what happens? What should we expect if something happens like this?
First of all, this is the asymmetry of the spectrum is essential. I believe that, I mean, I don't know if there are other, I'm not aware of other examples with similar asymmetry in the higher Landau levels.
Mm-hmm.
I would say I would not expect that, because the asymmetry, part of the issue with the lowest Landau level is that they are the dimension, they have a lower dimension, right? Because it's only depending on the PZ momentum. So the lower dimensionality of the lowest Landau level, I think is key. It's not the only thing, because you have this, the effect of the magnetic field in the lowest Landau level is that it creates, it's 1+1 dimensional, right?
Yes.
Always. But you don't have asymmetric modes regularly. So the asymmetry is an interplay between the presence of the magnetic field that decreases the dimensionality of that Landau level, in particular the zero Landau level, and the density wave type of solution that you have. So it's an interplay between these two things. I would say that this probably has to do, this is a little bit hand waving, but I think it has to do with the fact that for the lowest Landau level, you have like the Fermi surface are the 2 points.
Yes.
And that will contribute to, it's similar to 1+1 dimensional theories, Nambu-Urano in 2 dimensions, or 1+1 dimensions, and they also have an asymmetric spectrum. So in 1+1 dimension, you have an asymmetric spectrum like this for 2-dimensional Nambu-Urano theory. And the magnetic field, this is not 1+1, this is 3+1, but the magnetic field reduces the dimension of the lowest Landau level, and that combined with the condensate, the density wave, is what produces this asymmetry. And the symmetry is key for all the properties, because the symmetry is the one that explains the presence of all these anomalous terms.
Yes.
I would say even for the fluctuations, the symmetry is key, because not only you have what I call the A1 terms, right? But also you have the B coefficients that are directly related to the lowest Landau level. And those are robust, because topology is very robust against perturbations. So I think that the asymmetry is, it's very important in this case.
Okay. And another question is, what kind of observable do you expect either in the quark matter when we have some kind of experiments and so on? How can you check it? What kind of observable do we expect? For this phase, I mean.
I don't have, my hope, let me put it this way. I have the hope that with new observations, we will learn more about thermal properties of stars, and the cooling curve, the thermal properties related to the star. Like, for example, this thing that I mentioned that we just did it, and we are writing the paper as now, where we saw that constraint on the heat capacity of the core is satisfied. So things like that. Ideally, you want to have a prediction of an observable. I mean, the ideal situation is if we come out with a prediction and we say, okay, we see this signal, an electromagnetic signal that has some imprint of the thermal properties or the electromagnetic properties, but somehow the transport properties of the star. If you see that, that means MDCDW. That would be ideal. I don't think we are so near to that, but so it's hard for me to say. I don't know. I wish I would have. I wish I would have an answer to that. Maybe you can help me to find an answer to that.
Yeah.
Let me add something else. That is, now we are also working in a possibility that with this phase, we can explain some of the weird observations that are known in the physics of magnetars. We are going to publish it very soon. Not to publish, that is to send for publication very soon, that paper. And I will be talking in the future if you have interest about that here.
Yeah, sure. It would be great. Yeah. Okay, any other question?
Yes, I have a question. Sorry, I don't have I don't have a hand.
A virtual hand.
Yes.
You don't
actually
have hand.
They have a hand?
Yeah. I'm not chiral, actually. My question is about the magnitude of the magnetic field that is required. I mean, is it relevant, the magnitude of the magnetic field, compared to something with the same dimension in this setup, for the effects to be observable, for example, to be significant?
That's a very good question. The good thing I would say about this phase, and I think it has also probably to do with the topology, is that you don't need crazily big magnetic fields for this phase to be realizing. You need, of course, the magnetic field, because you're talking about Landau quantization. So the magnetic field has to be at least over the critical field for the mass of the quasiparticles there. But the mass of the quasiparticles is this parameter here, right, in this graph. So it's not very high. So I would say magnetic fields of the order of 10 to the 17, this is a little higher than that, but not very too far. 10 to the 17 would be fun for this phase to be realized, and for all these observations or these properties that I mentioned to exist. So this is another thing that makes this phase particularly interesting, because most of the effects related to a magnetic field requires huge magnetic fields. A lot of, I mean, we have done, Frank and I, we have worked a lot on that. And for example, if you look at the equation of a state, you really need huge magnetic fields to see a direct effect of the magnetic field, you know, the magnetization in the equation of a state. But those huge magnetic fields are, you know, they can be predicted on theoretical arguments, but they are not very, because then you have issues with the stability of the star, with the huge magnetic fields, etc. So the good thing about this phase is that, no, the magnetic field only needs to be over the critical value for the mass. And the mass can go, you know, the mass is not very high in this region. In this region, this is not a region of interest because these are not the star densities. The densities of interest are in this part here. And for them, the mass goes down. So the magnetic field actually doesn't really have to be very high. So 10 to the 17, up to 10 to 18, but 10 to the 17, I would say is fine. And that's a reasonable field for the core.
Yeah, so essentially you are comparing the magnetic field with this mass.
Yes.
And there's nothing, it has nothing to do with the gravitational energy that is available in the neutron star, yeah?
Yes, I'm not introducing here the general relativity or no.
Okay. We have two questions in the chat. I think you'd see them. You can see them.
See them.
I can read them both
Okay.
from Kazem Bitaksir. Dr. Bitaksir is our colleague. He says that, is there any gravitational wave evidence for such topological effects?
Is there any gravitational wave?
Evidence.
Oh, well, so far not. I mean, the gravitational wave, as far as I understand, they are producing constraints on the tidal deformability of the stars. You know, you can, and that is part of the argument that was used by this group of authors when they did the analysis of whether there is or not quark matter in the core of some neutron stars. I don't think there is anything I can connect directly right now, but the equation of a state would be constrained by the tidal deformability. So we need to consider that. And we haven't done. This is another work that we are interested and see if there is any issues with consistency. But as I said, I hope that more measures, the measures will be more sophisticated from merging of objects, neutron stars, or maybe neutron stars are black holes. And when that becomes available, we will have to see. I mean, this is one question that is important. Is this phase and the equation of a state that its phase has? I mean, we already saw the two solar masses, but what about the tidal deformability? Is that consistent or not? And of course, you have to also be careful because if those masses, those stars, you know, if they correspond to 1.4 or about that neutron stars, maybe that's not where the phase is realized, but maybe a two solar mass or near two solar masses is more viable for this phase. But this is an important question and we need to think about it. Particularly, we need to consider, you know, work on that in the future.
Mm-hmm.
So I think the other question in the chat is already answered, and therefore, if there's no other question, I will stop the recording. And people
Thank you.
So thank you very much. If there is no other question, I will also stop the session.
Thank you very much. I enjoyed the seminar. I hope that it answers some of your question and inspire some